Alright, so gonna run a quick video on respiration and the Krebs cycle and all that. So essentially we've got to start with glycolysis, which is pretty chill. Glycolysis, just some key points before getting into what it actually is it occurs in the cytoplasm and is anaerobic. Not really sure how that's spelled, but anaerobic means does not require oxygen. Okay, so glycolysis, you start with your glucose molecule, which is obviously 6 carbon, 1, 2, 3, 4, 5, 6. Okay, that glucose molecule gets phosphorylized, which involves 2 ATP to 2 ADP. Now, if we recall, ATP hydrolysis or ATP breaking up is ATP to ADP plus an inorganic phosphate, sometimes written with a little I. So if that's what's happened here, and there's 2 of them, so there's 2 ATPs, right? That means there must be 2 inorganic phosphates swimming around. What happens to those 2 inorganic phosphates is that they actually just jump right on the end. So we still have this 6 carbon. I'm just going to draw it again, but now do an orange, 2 phosphates because of that 2. There's 1 on the end here and 1 on the end here. So that's a phosphate, by the way. Okay, then this splits. So this is the lysis part. So lysis. Okay, we've got 1, 2, 3, and a P on the end. And 1, 2, 3, and a P on the end. Okay, so we can just see how that has literally split right here. Okay, then pretty simple, an inorganic phosphate just joins. So we have another P swimming around, don't need to know where or why, and they just join on. Okay, and logically that makes this molecule. 3 of these, another phosphate. So that's what happened when the P joined on this side, and obviously this side is just the exact same. So this just needs to be memorized, by the way. It's just the steps of glycolysis occurring in the cytoplasm, does not require oxygen. Okay, so that's what we have so far. By the way, this was a 6 carbon and it's just glucose. That will be fine in the mark scheme. Okay, then what happens with this is, oh, by the way, I've seen multiple choice where it's like, what does the phosphorylation of molecules do? It makes them more unstable. It makes the activation energy lower, so all this stuff is more likely to happen. Okay, then this. By the way, you only need to memorize like one side of glycolysis because it's the same. Once you split it, the same thing happens to both sides of this molecule. So what we have here is NAD plus. Okay, it's not NADP. The P is for photosynthesis because photosynthesis starts with P. In respiration, it's just NAD. So that needs to be remembered. Gets reduced to NADH. Okay, and you can write the plus H if you want, plus H plus here, because that's what the full equation is, but that will be fine. And then also, we can kind of think back to that logic from before about the ATP. 2 ADP become 2 ATP, which means we had 2 of these, and then it became 2 of these, so we must have added 2 of these phosphates. And where did these phosphates come from? Well, they're sitting on the ends right here. So if we take 1 phosphate off for 1 ADP and get 1 ATP, then we take another phosphate off and we end up with 2 ATP right here. We've just shaved both P's off to get 2 ATP, which means we're just left with this 3 carbon thing. Now this you do need to know the name of. It is called pyruvate. Pyruvate. Okay. same thing happens here. Okay, NAD plus gets reduced, and 2 ADPs snatch these phosphates and become 2 ATPs. Now, another mark scheme point to mention is how many ATPs do we have here? We have 2 ATPs here. We have 2 ATPs here. Okay, so we've got 4 ATPs. We've just produced 4 ATPs. But how many ATPs did we spend? Well, we spent 2 here to phosphorylize this, which means up here we spent 2 ATP, but down here we gained 4 ATP. So if we spent 2 but got 4, we have a net gain of 2 ATP. And we got 2 pyruvate, and all of this happens in the cytoplasm with no need of oxygen. Okay, that's glycolysis done. After glycolysis, we have the link reaction. So the link reaction. Okay, the link reaction, basically what happens is pyruvate gets decarboxylated. So we have this pyruvate right here, 3 carbons, okay, decarboxylated, which means the definition of decarboxylation is a carbon leaving, and it leaves in the form of carbon dioxide. So this is a CO2 molecule, decarboxylation, okay. This is decarboxylation, just means it's losing a carbon, and in this case in the form of CO2. Okay, and also again NAD plus is reduced to NADH. The reason for this is there's electrons in these bonds, and when you break them they have to go somewhere, right? They have to reduce something, and that's what NAD plus does. It gets reduced. Decarboxylation, a carbon leaves, and this 2-carbon compound gets picked up by coenzyme A. So what you end up with is this 2-carbon compound and then this coenzyme A, and this thing is called acetyl-CoA. Okay, link reaction. This happens in the mitochondrial matrix. Okay, mitochondrial matrix, which is kind of that like inner area, that cytoplasm, if you will, of the mitochondria. Okay, then this is the Krebs cycle. This is like the real kind of heavy part of do in a different color, green. Actually, no, that looks like photosynthesis then. Galaxy. This is the, actually no, that's weird. Okay, Krebs cycle. Okay, this is like the real thing to memorize. So we got acetyl-CoA. One thing we can't get mixed up about here is we actually have 2 of these because we got 2 pyruvates, but I only drew it for 1, and you only draw the Krebs cycle for 1. So it's important to know that the Krebs cycle actually does go around twice for 1 molecule of glucose, because we kind of end up doing this goes around twice when we get 2 pyruvates. Okay, and then in turn we get 2 acetyl-CoAs, and then a Krebs cycle is for 1 acetyl-CoA, so the Krebs cycle happens twice, right? So what we end up with is this 4-carbon compound. This is what the Krebs cycle starts with. If we remember, photosynthesis carbon cycle started with RUBP. Krebs cycle starts with this 4-carbon compound. That's all we need to know. Okay, we just need to know it's 4-carbon compound. We don't need to know a name. We don't need to know anything else like that. This 4-carbon compound gets picks up acetyl-CoA, which we had from before. Okay, so that's pretty chill. That becomes, we need to know that here acetyl-CoA is no longer needed. Okay, so acetyl-CoA dips right out, and you can just write that. Remember, the annotations help in extended responses and questions for this. So acetyl CoA no longer needed. Okay, that's pretty calm. And what we can imagine here is a 4-carbon compound binds with something with a 2-carbon compound, and the coenzyme A leaves. So logically, 4-carbon compound plus 2-carbon compound minus the CoA is just a plain and simple 6-carbon compound. 4 plus 2 is 6, right? 6, yeah. 6-carbon compound. We don't need to know the name of this. It's chill. Okay. If we notice, 2 of these carbons are from the original glucose. So most of these, only 2 of these actually survived from the original glucose. Most of these are from the 4-carbon compound. All right. Then, the 2 next steps are repetitive. They are decarboxylation again, and the reduction of NAD+. Wherever decarboxylation happens, the reduction of NAD will happen because, like we said, we're losing that bond. And decarboxylation in the form of CO2. Again, if we just lost a carbon, 6 minus 1 is a 5-carbon compound. And the same step happens. Again, decarboxylation. It's the reduction of this to this, and a CO2 leaves. Okay, just say this is decarboxylation for that mark scheme annotation, and this is also decarboxylation. You can say the 5-carbon compound gets decarboxylated, and up here you can say the 6-carbon compound gets decarboxylated. So logically, if a 5-carbon compound gets decarboxylated, losing a carbon, it becomes a 4-carbon compound. 4-carbon compound. Okay, then we just draw a nice long arrow back to the 4-carbon compound, because that's what we had before. And here we have the reduction of a few things. First off, just to memorize these, we have an ADP plus a P, that inorganic phosphate becomes ATP. Then we have FAD becomes FADH2. This FADH2, it's an electron carrier, right? It's not in photosynthesis. It's new to respiration. Actually, neither of these are in photosynthesis because we remember it's just NAD, not NADP. And then we have NAD plus to NADH. You can also say in mark schemes reduced NAD. You don't actually need to remember that it's becomes NADH, so reduced NAD is fine. But I just kind of like writing that. And yeah, that's the Krebs cycle done. Comment down below if you want to know what happens next with the electron transport chain. Thanks for watching.